All right, folks, just a quick video here today. We're going to reach into some physics concepts here. Some of this may be review in particular if you've taken physics. And we will, because of that, depending on your background, some of you may find this a little bit more challenging than others. Some may find it extremely straightforward. Some may find it very new, and either's fine. We're going to just get through it either way. Now, jumping in, we're going to leave a lot of the work here for in class when we return. But we'll go over at least a few definitions so we're prepared with those. So number one, speed and velocity. These are two things we're comparing. Looks like they really both should be bolded, but they're not, and that's all right. Speed is the rate at which distance changes with time. Okay, so if you think about it, when you're driving a car, if you say you're driving at 50 kilometers per hour, then we're saying 50 kilometers, right? Kilometers is a distance per hour, which is time. So we're comparing how distance changes with respect to time. Now, speed is a scalar quantity. That means that it has a number, it has a magnitude, 50 in this case, kilometers per hour, but it has no direction. So it does not matter if we're traveling 50 kilometers an hour and we're heading north, and our friend is traveling 50 kilometers and they're heading south, then we would say we're both traveling with the same speed, because the speed is the distance we're traveling over a certain time. Okay, now speed, the short form for speed that you will see is given by a v, and that's from physics. Often in here we'll write a v with a subscript avg, and that means average speed, okay? Average speed, which would be an average rate of change, an AROC, if you will. Now, velocity is the rate at which position changes. Now, position itself is not a scalar quantity like speed. Position is a vector quantity, meaning there's a direction involved with it. So velocity is the rate at which position changes with respect to time. Velocity is a vector quantity, and that position, or that direction, comes from the position part. It's a vector quantity, meaning that it has a magnitude and direction. And that means that if my position, so that's also a vector quantity, if my position is 12 kilometers north of my house, and my dog's position is 12 kilometers south of my house, it means we're in different positions, and that makes a whole lot of sense, right? But we are both the same distance away from the house. All right, so now since position is a vector quantity, so is displacement. Displacement is change in position. Okay, so in that example, my dog would be 14 kilometers. I think I said I was 10 and she was 4, I'm not sure, or 12 and 4. The dog would be 14 kilometers away from me. The displacement between my dog and I would be 14 kilometers, okay? Now, velocity is the change in position over time. Now we're going to leave example 1. We'll try and have some fun with that when we get back into class. We want to jump forward to example 2. Now, with example 2, we want to take an average speed. Speed, not velocity. Now, an average speed takes the total distance. So average speed takes the total distance, and we divide it by the amount of time elapsed. So from 0 seconds to 11 seconds, we know that the amount of time elapsed is 11 seconds, right? And if you will, we can take that as 11 minus 0, whichever you prefer. Now, the total distance from 0 to 11 seconds from this, we call it a displacement time graph. From 0 until 11 seconds, what's happened with this person, if you will, maybe a person's moving away from a motion sensor, they have moved 5 meters, right? Their distance here is 5 meters. They moved 5 meters away, and then they stayed there for a little bit. That's why it's constant. Their displacement from the sensor is not changing for, looks like 5 seconds here. And then they move back until 11 seconds, at which point they are 3 meters away. So my total distance traveled, that would be, that's kind of like, that's counted as if, as your odometer would count distance on your car. Okay, if your car travels away and then comes back home, then your car has traveled, even though your displacement has not changed because you come back to the same spot, your car has traveled a certain number of kilometers. So in this case, we're not just worried about how far our person is away from the sensor. We are worried about what is the total distance they've covered in that time. In this case, the total distance they've covered in that time is the 5 meters right here plus the 2 meters that they returned. Okay, so in this case, it's 5 plus 2, that's 7 meters. So 5 plus 2, if I'm being a little bit picky, I'll set this up like a physics teacher would, 5 meters plus 2 meters. Okay, now I'm running out of space, and I apologize for that, so I'm working sideways a little bit. That is 7 meters divided by 11 seconds, and we can throw that into our handy-dandy calculators because it's a because we're looking for context in here. So 7 divided by 11, we're working with 0.64 if I round, 0.64. And my units here, we don't need to memorize the units for speeds or velocities. My units are shown in here, right? In my numerator, I have meters. In my denominator, I have seconds. So that's meters divided by seconds, and that is meters per second. Okay, so that's our average speed. That's how we calculate that. We're taking the total amount of distance traveled. All right, now into the average velocity from 0 until 11 seconds. We care about the amount that our position has changed. Well, at 0 seconds, our position is 0 meters away from this sensor. At 11 seconds, our position is 3 meters away from the sensor. So our position has only changed, by 3 meters. Okay, so my average velocity, and I should have, I meant to show this up here. Your average velocity is often shown as VAVG, which looks a whole lot like speed. So we call it a harpoon or a hook. We put that on top here, and that means that it's a vector quantity, okay? So it means there's a direction involved. So here we would write the average velocity equals 5 meters minus 2 meters, because that is, they've traveled 5 meters here, and then we've come back the 2 meters. So 5 meters minus 2 meters divided by 11 seconds, and that is the 3 meters of distance here that we have traveled. That's we calculated already, divided by 11 seconds. And what we need here, 3 divided by 11, again, into our handy-dandy calculator, 0.27 approximately. 0.27, and again, our units are right there, meters per second, okay? Meters per second. Now the problem is velocity is a vector quantity, right? It has this harpoon, meaning we need a direction. So the direction here is that they have traveled 3 meters away from the sensor. So we must include that. If we do not include it, we're missing a piece of the answer. Velocity is described by a magnitude, and that's right here, and a direction right there. All right, you should be able to, whoops, I'm already showing the answer, and that's okay. You should be able to handle C and D here. I want you to try and calculate them on your own. This is the same image, just brought down here for your convenience. I want you to handle those on your own, and then we're going to push into the different shapes that can be involved in a position time graph. So if the slope of a tangent, I know I'm going pretty quickly, and that's okay. If the slope of a tangent or a secant on a position time graph. Now, this is a displacement time graph. They're effectively one and the same, okay? So on a position time graph, if our slope of a tangent or secant is positive, then the displacement will be positive. And that means that here, the slope is positive because it's going up, right? And if you're confused about that, think about y equals mx plus b, and maybe Google it if you're still confused. Okay, the slope is positive, so we would say here that our displacement is positive, right? We said our displacement was 5 meters here. We want to sketch 3 scenarios in which the position will always be increasing, i.e., that means that we're working with a positive displacement. So when we're thinking about that, I really want you to pause the video here and try and imagine 3 different shapes is what we're looking for that are always going up. And if you cannot think of them, think about our base functions that we've worked with. Some of them many of them have increasing intervals, but not all of those increasing intervals have the same shape. So I want you to try and come up with 3 different shapes that are increasing and then pause the video here and come back, and I'm going to show you the 3 different ways we can move here. So let's take a look. The very first one is with a constant velocity. That is, we're going to have a straight line here. This is because it's a straight line, that means our average rate of, or our rates of change remain constant. They remain the same. And if our rate of change remains the same, it means that the velocity would be the same throughout here. Okay, velocity is the same. This is positive displacement throughout. If you're confused by that, that's okay. It'll come with practice. Next, though, and again, as I look from left to right here, as I look from left to right, I can see this is increasing throughout. Next, though, I want to draw another one. This one looks like this. The kind of shape this is like an exponential function, say. This is what we call acceleration. Okay, so I should write this as the first one was constant velocity. The next one is acceleration. Now, I know it's acceleration, and I'll explain that here, because if I draw some tangents, I could say have a tangent there that looks like this, and at the beginning, the slope of my tangent looks much flatter, right? So this tangent, although it's positive here, it's only slightly positive. Over here, it's very, very positive, right? So my slope is increasing as I go along here. My slope of my secant is increasing. And that's what tells me it's acceleration. If the slope of the secant, and that is our velocity, and that is our rate of change of position, if our rate of change in position is positive here and it's positive here, but it goes from less to more positive, that means that we have acceleration. That means our speed, means our velocity are increasing here. Okay, and lastly, we can have deceleration. That's the opposite of acceleration. So acceleration is something speeding up. Deceleration is something slowing down. So that would be something like this. Okay, where where if we were to sketch a tangent on the curve at the beginning here, it would be very highly positive, and if we sketch a tangent on the curve near the end here, it's only slightly positive. Right? So our velocity goes from very high to much lower. Although position is increasing the whole time, it's increasing slower and slower and slower and slower and slower, and that's why we call it deceleration, because it's slowing down. Okay, if this is tough for your mind to comprehend, that's okay. I encourage you, rewind this, play it over and over and over again, and just think. Okay, we will talk about them in class. Next, if the slope of a tangent or a secant on a position time graph this time is negative, then our displacement is also negative. Okay, so we want to sketch 3 more scenarios in which our position is decreasing, i.e. negative displacement, and that could be described by something coming closer to a sensor or by a height decreasing. Okay, so again, I want you to pause the video here. Try it out. Sorry, folks, you get to hear a nice bell in the background. And then I want you to compare your work. Again, we can be working with constant velocity. Or we can be working with here. I want you to think, is this an acceleration or deceleration? What we have here, if we sketch the tangents, I have it going from steeper to less steep. And that means that I have deceleration. Deceleration. If you prefer, you can sketch these in the other order, so it lines up your accelerations and decelerations. But this would be deceleration because our rate of change. Sorry, folks, that's what I get for recording in the school here. But I'm hoping they're not too intrusive to the video. Lastly, we can have acceleration. Something can accelerate even if it's returning to a sensor, or if it's falling, right? So let's, for example, this would be something like, say there's a vehicle and it's far away from you, then its position might be decreasing if it's heading towards you, right? If its position relative to you would be decreasing if it's coming towards you, but they can be speeding up as they come towards you, which would look something like this, where its tangent is only slightly negative, and that gradually changes to become much more negative, so it would be accelerating. All right, again, if those confuse you, that's okay, we'll get there. Next, I want to take a look. You should be able to handle something like 3a, but I want to take a look at something like 3b, so we'll try that together. Okay, we're trying to draw a graph of the scenario that's going on. We want to start 10 meters away from the point of origin, so we'll go up 10. We'll say start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome, I left enough space for us. 10 meters away we start, and I do appreciate your patience from those chimes. We start 10 meters away, so we start right here, and we return, so we're coming back to the point of origin. We return at an increasing rate. Okay, so we're getting closer and closer to the point of origin, but our speed is increasing. Okay, so the rate at which we are moving will be increasing as we go along. So our general shape, I want you to pause and try it out. Our general shape should be something along the lines of this. It's increasing, increasing, getting steeper and steeper and steeper. Okay, so just because we have our distance changing does not mean it needs to be at a constant rate. Sometimes it's increasing, sometimes it's decreasing. Next, let me see here. I'm going to handle 4A, B, and C, and I'll ask you to do 4D on your own. And you know what, actually, you should be ready to handle all of A, B, and C. So try them out. If you can, great. If not, then that's okay. There are 3 parts to this, so I want you to try and calculate 3 average velocities. The first interval being A, the second interval being B, the third interval being C. And remember, if you're calculating velocity, then you need a magnitude. That is a number, magnitude, and direction. Okay, I know there are a lot of new terms in this. It really sounds like a physics lesson. It's very related to physics. And lastly, if you're feeling, folks, if you are feeling great right now, try something like this. If you're not feeling great, wait until we go over this in class and then try it out, because this is a very fun, useful activity. Thank you. At this point, you should be nice and ready to handle quite a bit in here, and I'm hoping I kept it relatively short.